Now I'm going to introduce you to pointers. And because the topic is so difficult, I'm actually going to make several videos related to pointers. So pointers are arguably the most difficult topic in the C programming language. And certainly in an introductory programming course, I would consider them to be the most difficult topic. But they're an important topic because in the C programming language, there are many things that either we can't do without using pointers or couldn't do easily without using pointers. And in my opinion, you really can't tell people that you can program in C if you can't use pointers. Before we define a pointer though, let's talk about memory and addressing. Everything that is stored in memory has to have an associated address so we can find that thing. Even something as simple as prompting the user for a year value involves addressing. So all I show you is one line of code, and we assume here that I've created a variable called year that's some type of integer. I know it's some type of integer because I use %d right here, but I've created this variable year here, and I want to use the scanf function to get the year value that the user types in. The problem is that the scanf function doesn't know about year. In my functions video, I talked about the concept of variable scope, and that has to do with where a variable is known at and where is it not known at. In this case, if I had written right here, int year, well then scanf doesn't know where it's at. So how can scanf then put a value there? Well, I pass it the address of the year variable, and I do that by writing the ampersand here. So there are several contexts in C in which you can use an ampersand, but in this context, where we're getting the address of a variable, it's called the address operator. So here's some code where I create a variable x of type int. It doesn't matter whether or not I've assigned an initial value to it. This alone sets aside some spot in memory for an integer, and that spot will have an address. I can see its address by typing in $x here. So when I run this code, it says the address where x will store its value is, and it wrote this value here. And notice I used the %p format specifier for printing an address. So I told you this is the address, but what form is this? Well, this is a hexadecimal number, or base 16. One of the ways I know that is because I see the letters B, F, C, and A mixed in with the numbers. But keep in mind that the number that has the digits 1, 2, 3, 4, 5, 6, 7, 8 could also be a valid hexadecimal number. So how do I know that that number is hexadecimal as opposed to base 10? Well, if it's a hexadecimal number, it's preceded by 0x. And in fact, you could create a variable that's hexadecimal if you wanted to by writing it as 0x followed by something else. While we're here, let's look at something in terms of format specifiers. So I created another video called Bits, Bytes, and Number Bases. And in that video, I took the base 10 number, let's say it's A is equal to 164. I took 164 and converted it to base 16 as an example. But if I write the code here, I can actually have it tell me what the base 16 equivalent is. So let's do this. A is equal to %d. This will give me A in base 10, but if I put an x here in lowercase, I will get it in hexadecimal. And if I write the x in uppercase, I also will get it in hexadecimal. Let's see that. So in that video, we found that 164, the base 10 number 164, when written as a hexadecimal number, was A4. As you can see here, the only difference between these last two lines is the case of the A, lowercase or uppercase. And so that's what the difference between the lowercase x and the uppercase x gives us. But A4, regardless of which way you write it, is the base 16 equivalent of the base 10 number 164. So you can use that as a way to test your ability to convert base 10 numbers to base 16 if you wish to. All right? So now let's define pointers. A pointer is a variable whose purpose is to store the address of something. So here I've created an int called num, and I gave an initial value of 3, and then I create a pointer to an int by writing int star as the type. So int star is the type. And I've chosen to write it this way, int no space star space num pointer, but it would be also fine to write int space star space num pointer. And also you could write int space star no space num pointer. So sometimes I put the star on the int, and sometimes I put it on the pointer variable name, depending on the context in which I expect to use it. Because in terms of how I think about the program, it may help me better understand what I'm doing. But any of those three options I gave you are fine. So here I've created a variable called num pointer that will store the address of an int, but it's uninitialized. So at this point, technically num pointer contains garbage values. Just like if I said int num semicolon, I would assume num had garbage values. So I can print the content of num, which is 3, and I can print the address of num by writing ampersand num. And here I'm just going to talk about the last 4 parts of this instead of saying the whole number, but it has address BBA4. Well, now if I want to store that address in the num pointer, I can assign it by writing num pointer equals ampersand num. And now when I say what is the content of num pointer, we can see it's the BBA4. So let's see what I just did. So when I write int num equals 3, I got a spot in memory called num, or that's how we'll refer to it since I don't care about the actual address in most cases. I gave an initial value of 3, but the address for this time when I ran it was BBA4. If I ran it again, I get a different address, but I don't really care in the vast majority of cases. So then I create a variable called num pointer of type int star, or pointer to int is another way of saying it, but it's uninitialized. So here's num pointer. It has its own address, which I didn't check to see what it was because I don't care. But right now we have garbage right here. There's some bit pattern associated with this, but I don't know what it is, and once again I don't really care. When I write this, num pointer equals ampersand num, now I said take the address of num, BBA4, and assign it to num pointer. And that's how that works. So what's the point of all that? No pun intended. Well, I would never really do this. I mean, if all this code is together, well then I would just use num to work with the value of 3. I don't care about the pointer. As we'll see later, there's places where I have to store an address, like in the scanf function we saw earlier, or I'll have the pointer somewhere else where I don't know about num, and that's where I would use it. But once again, in order to keep everything together, let's see how I could actually use the pointer. So here I've created num, gave it an initial value of 3. I've created a pointer to an int, and in this case I chose to go ahead and initialize it with the address of num. I could have done it later, but here I did it at the time I created num. So I'll print num, a num pointer, but how do I know, or how do I use num pointer to work with the value of 3, which is what I actually care about? To do that, I dereference the pointer by writing star num pointer. So here, I'm creating a variable that points to an int. Here, I'm using that pointer to get the int. So having a star in each location is a slightly different use. So if I just wrote num pointer, I would have the address for num, but star num pointer gives me what's at that address, which is 3. Now I want to assign a new value to num, but I'm going to use the pointer to do that. So star num pointer equals 99, and now when I print num, I can see it's 99. Let's see what I just did. So let's assume I did basically the same things, except now when I wrote int star num pointer equals ampersand num, I gave it this right here. And then when I write star num pointer equals 99, now replace the 3 with the 99. So I could have said num equals 99 to get that result, or star num pointer to get that result, because my pointer points at this memory address because that's what's stored there. And star num pointer lets me work with that address. That's what's going on. Once I have a pointer variable and have it initialized, I can use it much the same way I would other types of variables. So here I'm going to create two ints, a and b, and I give them both an initial value of 3. But then I'm going to go through and do several different things to a, and then I'm going to use a pointer to b to do the same type thing to b. That is, do the same thing to the memory address that b references. So here I have the address of b stored in b pointer. And if I want to add 4 to a, I can do a plus equal 4. And if I want to add 4 to b, I can use star b pointer plus equal 4. So we can see here that a and b are both 7. What if I want to increment by 1? I could have said a plus equal 1 in both cases, or star b pointer plus equal 1 for the second one. But I can use the increment operator as well if I want. So here I wrote a plus plus, and that incremented a up to 8. And then when I write star b pointer inside parentheses and then increment it, I incremented b by 1 up to 8. So why are the parentheses here? It's legal to write star b pointer plus plus without the parentheses. The problem is that does something different from what I expect. If you look at the C precedence table, you'll see the postfix operator, which is where I'm using the plus plus after the variable name. It has higher precedence than the star. So without the parentheses, it would be equivalent to writing inside parentheses b pointer plus plus and then dereferencing that. The problem with that is it says increment the pointer and then use what's at that address, which is not what we want. So here, the parentheses are required. I personally don't like writing something like this because it's too easy to make a mistake, in my opinion. And there's many opportunities to make a mistake with pointers without me adding to the opportunity. So pointers are variables themselves, which means they have their own type. So it was decided not to have a type called pointer. So we can't write pointer num pointer. Instead, a pointer points at a certain type of variable. When I write int star num pointer, this means it points at an int, not a char, not a double. If I want to point at a double, then I would have double star. If I want to point at a char, I'd write char star, or other varieties actually. We need to make sure the type matches. Now, technically, I could compile code that didn't do it correctly, but when I tried to do certain things with the pointer, then it wouldn't work right. We also can have pointers store the address of another pointer. So let's see how this works. So let's write some code that creates these 3 variables and then print some things to see how it works. Okay, let's do this 3 times. So here I chose to put the stars next to the variable name. It doesn't matter. And I'm doing this sort of in reverse order to keep things lined up. And this was BEP, right? So there I've created those 3 different variables and I've initialized all 3 of those variables. Let's print out a bunch of things. These will need to be P's now because I'm about to print a bunch of addresses. Right. So what's the relationship here? As we'll see, these three lines all do the same thing, or give me the same value. These three lines give me the same value. These two lines give me the same value. And then this is just here for completeness. So we're going to compile that code, assuming I did it correctly. And now let's run it. And notice that each time I run it, these are addresses. I get different addresses. And I would expect that to keep happening. And I would expect when you run it to get different addresses than I got, because it's the job of the operating system to decide where to put things in memory. As a user, I don't have a lot of control over that. There's certainly some cases where the programmer needs to make those types of decisions. In particular, if you're writing operating system code itself, you might need to decide that. But for most of the code I write, I don't really have a say in where I put things, nor do I care. So let's work with these values here. Right? And let's write down what we did here and then draw a picture and show you what's taking place. So I created a variable called num and gave it a value of 5. And based on the last example I had, the last 4 characters of the address were EFDC. So this is address EFDC. When I wrote int star AP ampersand num, then I stored this address in this pointer. But AP had its own address, EFD0, which I stored in BP. So BP points at this memory address. So this is EFD0. And then finally we saw that EFC8 is the address of BP. So what's happening? When I write num, I get the value 5. AP contains the address of the num variable. So when I dereference AP, I also get 5. So I'll write arrows here to show what the output is. When I write star star BP, we saw that I also got 5 because I'm basically jumping. The first star says dereference BP to get what's at address EFD0, which is this. The second star then says, okay, now dereference what's at this address, which is EFDC, to get what's at there, which is a 5. So these are equivalent. When I write ampersand num, we saw that I got EFDC, which is stored in variable AP. And to get what is at address EFD0, which is EFDC, I can dereference BP because it contains that address. So this was this. BP contains the address of AP, so I get EFD0 here. And to get that address of AP, I can write ampersand AP. Get EFD0. All right. So another thing to keep in mind is that writing star star BP and star BP, and this is BP, sorry. Each of those technically represents a different type. So let's look at a way to think about that actually had a student show me many years ago. So let's say we create the variable this way, int star star, and we'll even put a third star. I've done things like this before, P. when I use, so the variable being used is this. When I write P, it's of type int star star star. And how do I know that? Let's come back over here and look at the variable declaration. When I wrote down just P, what remained to the left of that int star star star, which is this? If I write down star P, which I could use in some places, what remains to the left? Int star star. When I write in my code star star P, or excuse me, star star P, excuse me, just 2 stars, what remains? Int star. And finally, when I write in my code star star P, what remains is just the int. So each of these technically represents a different type. So if you could ask your computer, what type do you think P is, or what do you think star star P is, these would be the answers in this case. Now you can't necessarily directly ask the computer what it thinks it is, but as you'll find out if you do much programming using pointers, many of your mistakes will lead the compiler to tell you it's the wrong type. And that's kind of how you'll know that it really wasn't an int or whatever. Each of these first 3 is an address, but they're the address of different types of objects. P is the address of a pointer to a pointer to a pointer to an int. Star P is the address of a pointer to an int. Star star P is a pointer to an int, or the address of that. And finally, star star P is just an int. Like up here, num was just 5, or star AP was just 5, or star star BP was just 5. Each of these, if you were to ask the computer, what type do you think that is? It would tell you all 3 of these are ints, and they give you 5. So you need to think about this when you're writing your code. Another thing to make sure you are aware of is be careful about comparing the values stored in pointers and what the pointers are pointing at. So let's write down this code and see an example. So let's say I create a variable int a equals 7. So I've got a spot in memory. I call a, and let's say its address is bf00 and its initial value is 7. And I wrote int b equals 7. So I got b. It has its own address. Let's say it's AA08 and its initial value is 7. When I write int star num pointer, and we'll initialize it to the address of a, that's a, this is num pointer, and it stores bf00, and when I write int star val pointer equals ampersand b, it stored AA08, so this is val pointer. So now if I write if num pointer equal val pointer, and then do something if that's true, what am I comparing? I'm comparing bf00 to AA08. So this is false. But when I write if star num pointer equal star val pointer, and do something if that's true, what am I comparing? I'm comparing what they each point to, which currently are spots in memory that contain the values 7 and 7. So this is true. If when I had written this, I instead had given val pointer the address of A, which is perfectly fine, I could have done that, then val pointer would have pointed to this, so it would have contained BF00, and num pointer would be equal to val pointer. So it would have had true in that case. And then this, of course, then has to be true because they're both pointing to the same memory location. This can't help but be true in this case. All right? So just be careful when doing that type of thing. So now we're going to get to a more practical use of pointers than what I've shown you before. As I stated previously, a lot of the code I showed you where I created a variable and then immediately created a pointer to that variable, I would never really do that at that location. Now we're about to see situations where I really do need to use it. Recall that when we discussed functions, we said that if I create this variable x right here with an initial value of 3, and then I call do something, giving it x, what I'm really doing is passing in the number 3. And this is a process called pass by value. But the do something function does not know about x, and therefore do something can't change the value of x. So in this case, if I'd wanted do something to actually give a new value to x, what I would have written is x equals do something x. That would be a way of changing it without knowing about x. But once again, the idea of variable scope is what's at play here. What if we do want, though, for the function to be able to work with the original variable? Well, then I can pass the address to the function, which is what we did when we started off by talking about scanf. And when I do that, we call that process pass by reference. I'm passing in the address of the variable so my function can know where to get something or manipulate something. So here I've created a program that creates an int called num with an initial value of 8, and we can print that and see that it's value of 8. But I want a function to change num to be 3 times its initial value. So I want it to be 24. So I do that by passing in the address of num. Down here, I have a variable called int star a pointer. So effectively, what I've written is int star a pointer equals ampersand num. That's how I initialize a pointer to have whatever num's address is, which I don't know what it is, nor did I care in this case. But now that I've stored that address, when I use star a pointer, I'm referring back to this address. So star a pointer is essentially another name for that memory address, which up here I refer to that memory address by using num. When I write star a pointer equals 3 times star a pointer, I'm writing 3 times 8, reassigning it to this memory address. And so now when I return back up to main and continue on, when I print the value of num, we can see it's 24. If I'd created a pointer up here, in order to initialize it, I would have said int star a pointer equals ampersand num, which is essentially what I did here. All right? So let's see another example, one that deals with arrays. But actually, it's not so much concerned with the arrays, that just is where we're storing our data. So we'll create an array called A, and it have these values: 13 minus 25, 99, 62. And we're going to create another array called B. We'll make this 50 minus 14, 61 minus 70, 123, that number there, 0, 209. So I have 2 different arrays with 2 different number of elements. So if I want to process A, what I'm going to ultimately do is write code to find the min and max of A, and then I want to also be able to do it for B. So how would I do that? Well, I'm going to ultimately have a loop. So I'm going to have a loop counter, I, and then I want some type of length variable. So I'm going to say length initially is equal size of A divided by size of A sub 0. excuse me, a sub 0. All right. So what happens here? Now technically size of returns a variable type size underscore t, but I don't have to worry about, in this case, the value here exceeding an int in terms of what it can store. But what I'm doing here is getting the size of a in bytes, dividing it by the size of one element of a, and that will give me the number of elements in a. So we also need some min and max variables. So int min, max, because we want to find the min and max. And I want to initialize these. So how do I do that? Well, the scalable way that doesn't expect me to know really anything about the range of potential values is to just pick the first element of the array. So I'm going to say A0 here. And I'm going to do the same thing for max. So I'm going to have a loop. And on each iteration, I'm going to ask two questions. Is a sub I less than the min at this point? And if so, make that the new min. And then do the same thing for max. So now I use greater than, and we'll update the max variable. And when this is all done, I should have the min and max. So let's see these. Sorry, %d. And max is equal to %d. Let's see if that works, and then we'll talk about how we're going to deal with b. Minus 25 is the min, 99 is the max. So now I want to process b. Now, b has a different number of elements, so I need to update length. It has a different set of elements, so there's a different min and max here, so I need to change my initialization. I need to change this code to no longer say a, but instead say b. And I can do all that here, but one of the reasons we have functions is so I can take the same functionality and reuse it. So I want to put all this code up into a function. But there's a problem. I want my code to determine both the min and the max and be able to print it down here. I could print from there and then I wouldn't have that problem. But let's say that I want the function to find the min and max so I can use it for some purpose down here, which I'm just going to print it, but maybe I need to use it in some other calculations. So how do I deal with that? Well, up to now, I could have dealt with it by having an array down here that stored two integers, and I could have, if I wanted to, made the first element of the array be essentially the min of the array, and the second element of the array be the max, and then pass that array to my function, since functions get the address of an array that they're passed, and work with the array directly via the addressing. I could have done that and then just placed the elements there. But instead of that, I want to just pass in these two variables instead of using an array. So what do I need to do? Now, I think I mentioned in my functions video that while you can write code in one place and then once you have it working, move it to a function, but the analogy I use is that is like letting a vine grow in a fence. The longer the vine weaves itself through the fence, the harder it becomes to disentangle it, and making sure you caught everything that you're doing in the other spot. So it's really better just to write the function from scratch by thinking what is the input to the function and what is the output to the function. But I'm doing this here to show you how I'm going to take this same logic and alter it to use pointers. So we said my function is not going to return anything, so the return type is void, and we'll call this min and max. And what does it receive? It needs to receive an array, and I'll just call it D. It needs the size of the array. Let's call it size. And it needs the address of the min and max variables. So I'm going to have int star min pointer and int star max pointer. Now I could have called these min and max, but then it's easy to get confused between the mins that are ints and the mins up here that will be pointers to ints. So I'm going to call it min pointer, max pointer. And that's also helpful when I'm reading the code to make me more aware that I'm dealing with pointers as opposed to ints. So now this leads to the question, where do I want to do the initialization? Do I want to initialize up here or inside the function? So there's trade-offs involved whenever you do things like this. One of the benefits about moving this to the function is that the user doesn't have to know to do it. Because the user is thinking, I just want to know the min and max of this array, and I want to know the min and max of this array. I don't care how you find the min and max, because you could arguably choose other approaches. One would be to sort, and if you were to sort these numbers, the min would be on one end and max would be on the other. So I don't really need to do this same type of thing. If I choose to do that, then I'm letting the programmer who wrote the min and max function make those decisions. So I'm going to choose to go that route, which is initialize min and max down inside the function here. So the programmer doesn't have to worry about it, or this programmer doesn't worry about it. The user of the function, I should say. But we still need to calculate length up here for reasons I've talked about before. So I need to move all this. And what variables do I need inside this? Well, I need the I variable. So see here, I'm already encountering a problem with my vine growing in the fence. So now I gotta change this because I didn't think ahead to how I was going to unentangle it. So now I take this down here, and I think that's the only one of the variables I declared I need down here. And we're gonna have the function call. So min and max needs to know A, length of A, which is the number of elements, the address of min, and the address of max. And now I need to come down here and do what? Well, down here the array is called D, so everywhere I wrote A, I need to change that to D. So what I'm doing, since I used the Vim editors, I'm creating what's called a regular expression. So I'm going to say everywhere you see the letter A, replace it with the letter D. But since A can show up easily in other things, the G means globally, so everything online, I'm going to type in C to confirm, which lets me make decisions. So yes, no, yes, 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 no, no, yes. So now I'm using D down here. I could have called it A, even when I'm using B, but this makes it more clear, I think. So will this work as is? Well, no. Everywhere I wrote min and max, I need to at least have min pointer and max pointer, but there's also a problem in terms of how they're being used. Min pointer is not an int. Star min pointer is an int. So everywhere I wrote min, I need to have star min pointer. So we'll mark this. I'm going to use regular expression again, or attempt to. So min becomes star min pointer. And the star may mean something else here, so this may actually not work. I'm going to have to fix this. Okay, it's working. And let's do the same thing for max pointer. Oops, I didn't mark enough range. Let's do that again. Alright, so I think that's all correct. We'll find out. The compiler will let me know, of course. And then we'll talk about using for B. Oops, what's it telling me? So what mistake did I make? In the function, I call this size. So where I use length, that needs to be size. And this is what this told me here. So minus 25 and 99 are the values. So now let's reuse the code. So now I'm going to do this. But now I'm going to change that to B. B, and B. Minus 25 and 99 again. It says minus 70, so minus 14, minus 70. Okay, minus 70 is the smallest, and the max is 2134. Remember, I'm doing this to give me some flexibility. So instead of me as the human coming through and counting 4, I could have done that. I could have, right here, have written 4, and this is, looks like 8 numbers. I could have written 8 here. But what if I come up here and do this? Well, now I have to remember that I wrote 4 specifically down here to make sure this works correctly. So we got the new max. I just let the computer do the work. Let the computer do the work instead of use the human doing all the work. That's why we have computers. So I think this is a better example of where we're going to start using pointers. We'll see other possibilities. When I talk about dynamic memory allocation, we'll have to use pointers there in order to keep track of memory locations for blocks of memory. But this is certainly one of the places where pointers are often used, is to pass in multiple values and be able to change those values. And that's what I've done here. If you find videos like this helpful, please hit the subscribe button because that actually helps me as well.